All right, so this video is going to go over chemical kinetics, factors that influence chemical kinetics, which is basically just looking at how reactions occur, the speed in which they take place. Are they slow or are they fast? We measure reaction rates by examining some sort of variable that's changing. Typically, that's concentration. It could be for either your reactants or your products, but it could also be a pressure change. But it's similar to how fast you're traveling in a vehicle. Basically, it's just a change in whatever quantity is being measured over a period of time. For our reactants, those concentration changes are going to decrease because they're being consumed. So if we were just describing the quantity of reaction rate, it would be negative. And for products, it would be positive since they're being made. We can compare reaction rates between reactants and products using their stoichiometric ratios in a balanced equation. So here you have the Haber process for ammonia being made from nitrogen and hydrogen. I want to know what the relationship is between the production of ammonia and the consumption of hydrogen if nitrogen's consumption rate is 3 moles per liter per minute. So if I know what nitrogen's consumption is, and because nitrogen is a reactant, I could either write that with vocabulary to describe that it's being consumed, or I could rate it quantitatively with the negative sign in front. Either way, to find the rate of ammonia being produced, I can start with that amount of nitrogen and then use the stoichiometric ratios between nitrogen and ammonia in my balanced equation. Remember, molarity is moles per liter, so if you're doing this with the same amount of volume, their molarity ratios would be equivalent as well. So 1 molar nitrogen would be consumed for every 2 molar ammonia being produced. And when I multiply, I would get 6 molar per minute of ammonia is being produced, or positive 6 molar per minute. I also wanted to do this for hydrogen. You could start with the ammonia. I like to go back to what I was given, just because there's no debate about that value. And in case I made a mathematical error, I'd rather start with something that I know is absolutely guaranteed. So I'm starting with nitrogen, but you could do this with ammonia as well. The nitrogen ratio to hydrogen is 1 to 3. So the nitrogens cancel, the molarities canceled. I do my math and I get that for every 3 molar per minute of nitrogen being consumed, 9 molar per minute of hydrogen is consumed, or that value would be negative 9 molar per minute. So the collision model attempts to explain why it is that some reactions are going to take longer than others to proceed. In order for reactants to form products, they have to collide with one another. But not all collisions are going to result in a reaction being generated. Not all collisions are going to have enough energy to form that transition state or are going to have the correct orientation. And the example shown to you in that graph, you need 2 molecules of bromine, nitrogen, and oxygen to collide such that the bromine atoms are able to form or to begin to form a bond between the two halogens. So if they're not oriented right, if the oxygens were colliding with one another, that would not help us. You need to have enough energy to generate that collision with the right orientation. And the energy amount that is required to form that transition state is known as the activation energy. And according to Arrhenius, that has to be overcome for the reactants to transition into products. For some reactions, that value is going to be much steeper than others. So some factors that influence how quickly a reaction can occur include the concentration of your reactants. If you have more reactants present, you're more likely to have more collisions, and that's going to help to speed up your reaction rate. The particle size can also play a role. By having more available particles to interact, you are going to increase the number of collisions, which is going to increase the likelihood they're going to occur in the right orientation and give you more chances to help to build up the energy that's going to be needed to reach that threshold activation energy. When it's in a chunk form, only the outside surface is available for interactions. Those inside particles are not able to interact. with whatever they are combining with. So more surface area, more collisions, hopefully better orientation, and more energy to get you to the transition state more effectively. Temperature will also play a role. As you increase your temperature, your rate of reaction should also increase. It's going to increase your kinetic energy, which will increase the amount of energy associated with your collisions. Approximately 10 degrees Celsius increase will cause a doubling of your rate. And when you take a look at this graph below, I want you to notice that you have two temperatures that are being examined, T low and T high. And then I also want you to notice a line towards the end of the two graphs, the curves that are on it. Energy is on your x-axis, but then you see E act down there at the far right-hand side, your activation energy. That would be the threshold energy those particles need to reach to be able to achieve that transition state. So you've got your number of particles on your y-axis, and at the low temperature, you have a much steeper curve. You have more particles with the average energy at T low than you do at T high. But because the T high graph is broader, you see that you have many more particles that have reached or exceeded the activation energy threshold at T high than you have at T low. So more particles that have reached that point are going to be able to reach that transition state more quickly. And then finally, we have catalysts. Catalysts are the one factor that doesn't necessarily increase to cause a change in your reaction rate. They're just present. These are substances that are able to increase your reaction rate, but they are not truly changed as a result of the process. They can be used and then reformed again as a result of the reaction steps that are taken. They provide an alternate pathway that will require less activation energy, so they're like a shortcut. They either can form a different reaction intermediate that doesn't require as much activation energy, or they are able to stabilize a transition state more effectively. Some examples of catalysts include acid-base and surface catalysts. Acid-base catalysts help reactants to either lose or gain your protons, while surface catalysts are able to provide a source of new reaction intermediates, or sometimes increase the number of effective collisions by modifying that amount. Catalysts are also known as enzymes, specifically in biological reactions or biological processes. They bind to reactants in ways so that they can reduce the activation energy or to form intermediates that are going to require less energy in the slower steps of your reaction. We'll get into that more towards the end of this unit. So here are a couple of ways catalysts can influence your reaction rate. In this first graph, you see that you have a pink hill that is uncatalyzed, a pink pathway, and a blue pathway that is catalyzed. So by stabilizing the transition state, the catalyst requires less activation energy for that transition state to form, and therefore the reaction proceeds more quickly. You can also have a catalyst just provide a totally different pathway, but you'll notice that all of those hills that are making up that other pathway require less activation energy than the original reaction. So no matter which way the catalyst chooses to work, the entire goal is to reduce that activation energy component. And so here I have you drawing a rough sketch of what a energy diagram would look like for an energy change in the reaction of negative 10 kilojoules per mole. Delta E is like delta H, so because it's negative, that's the exothermic change. And EA is 50 kilojoules per mole. So if I go back to those graphs that I just showed you, you'll see delta E is on the graph on the left. Delta G is representing delta E over there on the right. You will have the graph come in one of two flavors. You'll always have the reactant starting out and the products ending. And if you're endothermic, because the reactants had to gain energy overall to form those products, the products line will be higher. While on an exothermic side of the graph, the products line will be lower because you had to release energy for that change to occur. Neither the reactants nor the products start at the origin on the x-axis because they bring to the reaction energy stored in their bonds due to any covalent or ionic bonds that have been formed. Only reactants that are elements in their standard states do not have energy values assigned to them initially. So if my delta E is negative 10, and this was a little bit hard to do on PowerPoint, I'm sorry about that. You would have the reactance line, just kind of see that there's a little line there at the very beginning of that graph. The reactance line would be higher than the products line because energy would be being released. The activation energy would be the energy the reactants need to climb the hill, 50 kilojoules. And again, delta E is the difference between your starting and your ending point on your graph. If this had been a positive 10 kilojoules, the products line would have ended higher than the reactants line, and delta E's 10 kilojoules would have been part of that activation energy arrow. It just would have been to the side of it.